So, good morning. My name is Amy Sullivan, and I'm the chair of the AAAR Endowment Committee. And it's my pleasure to welcome you to the 12th in our monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So with these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us an opportunity to come together outside of the annual conference. So each month, the editors of AS&T picked a high impact journal article to be presented by its author. These lectures are being recorded and they'll be posted to our new AAAR YouTube channel, which you can access from the AAAR webpage under the events tab. In addition, each month, one of our student chapters is serving as host. And so I want to thank everyone who's made all of these lectures possible and for all of you for joining us. And so with that, I'll turn it over to our student chapter from Washington University in St. Louis. Thanks.
Thank you, Amy. On behalf of Washington University in St. Louis's AAAR student chapter, I'd like to welcome everyone to our May 2022 lecture. Today we have Dr. Prathim Biswas. He is the Dean of Engineering at the University of Miami, and he also currently leads the Aerosol and Air Quality Research Lab. In today's lecture, he'll be discussing particle formation and growth in aerosol reactors, as well as particle collection systems. And with that, I'd like to turn it over to the speaker. Dr. Biswas, you have the floor. Go ahead.
Yeah, thank you, Abhay. Thank you, Amy. I think this is a great initiative of AAAR, and of course, it's a great pleasure to present to all of you one of our recent publications, though I broadened the title a little bit, just in the form of an introduction and referring to maybe aerosol reactors and aerosol reaction engineering. I presume everyone can hear me well and see the screen. So see my slides, so I'll proceed. Okay, so the outline, I will first, as I said, talk about aerosol reactors. It's sort of a general, present a general terminology. So really club the entire system, including engineered systems, other systems, which result in both intentionally producing particles and unintentionally producing particles. And I think both are important. Intentionally, of course, we do that for a specific application. Unintentionally, there are other consequences and hence the interest, okay? And of course, the commonality is, and I'll focus a little on the high temperature systems, and hence the transformation from a molecular state, vapor state, to a cluster state, to a particle state is what we define as aerosol growth dynamics. You could also throw in the word formation and growth dynamics. So I'll briefly allude to that. And then use this general terminology to define this system. Some of it might relate to an engineered system where we make these to produce particles, but then we also have these where you're doing something else with it, like producing electricity or combusting something or producing a chemical. And then the particles may not be of primary interest, but are of great impact and consequence. And the focus then will be on particle collection and the importance of charging, which of course is a key element of the growth dynamics. And I'm going to describe a plasma system with a DC bias that this paper describes to enhance particle charging. And the paper is listed below. It appeared, I think, last year, maybe 2 years ago now. So I'm going to refer primarily to that aspect and acknowledge the co-authors who actually did all the work. Sukrant Dhawan, Abhay, Girish Sharma, Abhay who's moderating today, Nabiel from now University of Illinois, and Dr. Mohan Sankaran, who really, we did this across campuses, and the collaboration really worked out well, bringing different expertise to bear. So another aspect that aerosol scientists we get engaged in, is do collaborative work. And this is a clear demonstration of that too. So let's continue. So if I look at a multitude of aerosol reactors, these are just pictures of laboratory scale reactors, mainly from my colleagues at Washington University. I can have a furnace reactor where I can externally control the temperature. And we use that to make materials such as graphene. I can have a flame reactor. I can have different modalities of flame reactor using different types of fuels, making different types of particles. And then I can also have things like dusty plasmas, which I might use to make particles. I just show this as a snapshot. And if I look at the industrial production of some material, this is a well-established use of, it may not be called an aerosol reactor, it might be called a gas phase reactor, but these are really scaled up. And if you look at the, I would even now refer to them as commodity production, titanium dioxide is produced maybe in 5 million tons per year, right? Carbon black, titanium dioxide is used everywhere. It's an additive to pigments. We make the particles in these reactors. And then, of course, there is a certain phase and a certain size that is desirable, let's say for light scattering properties. If it's used for other applications, there might be other crystal phases of importance and other sizes. Carbon black is added to all our tires, which prevent us from going in and changing tires every few months. They last for a much longer time. It increases the resilience of rubber, which makes up the tire, 8 million tons per year. Silicon is a very important semiconductor. It's made by a number of techniques, but gas phase techniques of some form or the other are also important. And once I bring in a silicon semiconductor, you can look at any electronic device, and this is a key component. Fumed silica is another one. So these are produced in large quantities. Of course, these are small scale reactors whose pictures I illustrate for doing maybe controlled studies so that we can dream up of new particles, new compositions. There are composites being produced, all kinds of nanomaterials for different kinds of applications. So if I continue, on the other hand, I show you now industrial scale illustrations, a lot of pictures here. So if you start from the top left, that's a picture of a rotary kiln, which is used to produce cement. And now look at the scale, right? It's 4.4 billion tons per year. This is also, of course, I'll put the tag of an aerosol reactor because it has a certain feed and then a high temperature system. And in this case, we might end up producing unwanted particles. Of course, the cement is like a powder material that is produced. So the product is also a particulate commodity, but then there might be all kinds of unwanted particles which are eventually emitted. And if you look at cement now, it's being really, the finger is being pointed towards cement kilns for even releasing large volumes of carbon dioxide, because fossil fuels are typically used to produce the heat that is necessary to produce the cement. And look at the scale, as I said, the previous chart, it was million tons per year. Here we are in the billion tons per year. And just pick on coal. I know coal is being beaten up and probably you need to better control it, but we really don't have an alternate yet. So we continue consuming coal, and there are other parts of the world that are developing. There is a transition from coal to natural gas, but even nonetheless, I think this is a number from last year or 2 years ago. 8 billion tons per year. While it's coming down, it's still being replaced by other fossil fuels. The renewables have to really catch up at a much faster rate. And if you look at coal, it is a very complex fuel, all kinds of particulate emissions. This has been studied for many years and so forth. And then interestingly, there are parts of the world where you still use coal for cooking or heating. I show you a nice small compact coal combustor. And of course, there is an exhaust that you can see at the top, and what is happening to all these emissions, right? And then pick another common material, steel. Steel is produced in large volumes. And again, if you just look at these images, you can see there's going to be a large cloud of particles that really need to be controlled, both for an occupational setting in case of steel production, but also eventually emissions. And a lot of advances are being made. So I'll use this general terminology to even put you sort of tag as an aerosol reactor, because that is what is of interest, at least to us. So in terms of a general terminology, molecules, if I'm talking of these high temperature systems, they would, as the gases cool, right, as they're leaving the reactor or the system, these molecules assemble. They then begin to form clusters. The clusters then grow. And as I said, again, intentionally or unintentionally, they end up producing nanoparticles. The understanding, we spend a lot of time trying to understand it, either to produce a functional nanoparticle, a desired nanoparticle, or an unwanted, or controlling an unwanted nanoparticle, right? Because we got to deal with it. And then the understanding might allow us to tune the size, shape, composition, properties for either good to make a material, repeating again, or to trap it and not let it go out. So there are twofold objectives. Again, I want to design a nanoparticle for functionality. I want to prevent emissions and even bring in the concepts of circularity. If I have a good understanding, instead of emitting something out, maybe is there any value to it? And I pick carbon dioxide, that's a gaseous commodity, of course, or gaseous species that is emitted. If I can somehow design a system to trap it, one, I begin to mitigate the problems downstream of things like climate change, but also close the loop and maybe reuse this. This is extremely challenging, but very topical area of study now. And I might use aerosol systems to do that, something that I'm not going to get into today. So if I look at this now, begin to put down what we sort of learn in a simple aerosol science class, start with the molecular state. There is a certain dimension of molecules. Then you begin to cluster this. One might refer to it as nucleation or the birth of particles. These clusters are dynamic. They can break apart. They can become stable and collide with each other, grow. So the collisional growth process is there. But then once I have a surface, even starting with a clean system, or I might have existing particles in the system, the surfaces act as a sink for some of these molecules. I might refer to that as condensational growth. That's also a kind of collision process, but molecule-particle collisions. And then all kinds of dynamics such as sintering, crystallization that take place, which gives me the eventual distribution that I end up with. And one has to get into detail if we are really trying to understand this. On top of this might be the charging characteristics, the composition that I'm not illustrating there, which of course are very important. So in addition to physical characteristics that I illustrate here, the chemical characteristics, the charge that these particles carry, the shape. These are all important parameters that one needs to track. So we put all of these together, we develop models, and this has been going on for many years now. Some simplistic models like monodisperse models, which means you just say that I'm going to track a mean size. The reason we do that, because it could be quite complex computationally, and sometimes a simple model might work. Then a log normally distributed aerosol, because many times these size distributions evolve into log normal shapes. Maybe we can use that. More detailed representation using a sectional form, which means you split the entire size range into sections. Then to more accurately track the initial steps of particle formation, discrete sectional models came in. Of course, the discrete representation would be the most accurate, but even today you run out of computing horsepower to really run that for a broad spectrum of size ranges. So you combine the discrete with the sectional model, and then there are other kinds. People get into molecular modeling approaches, Monte Carlo approaches, and so forth. And one wants to compare these. There's no single model that would be perfect for every situation. So people compare these and then use them accordingly. And there's a large literature base. This is just a snapshot of some papers that I illustrate here. Okay, so let's get on and now start diving into this, what my so-called aerosol reactor system. What are the components? And then, of course, I want to transition to the topic of the paper. So if I look at a reactor system, I'm interested in understanding, and I say nanoparticles because it's the initial stages of the particle that it ends up. And more often than not, those are the size ranges in which particles are emitted, especially from a high temperature system. Of course, there are many others like dust and all kinds of processes that I'm not getting into here. So more looking at this pathway. So I need to understand, what kind of precursors come in, or what is the feed into the system. We have a great interest in this capture and control, right? And of course, we have tremendous instrumentation, real-time instrumentation, some of it pulling a slipstream out because these are really concentrated systems. So we need some very precise sampling type of systems, but much of these are also being miniaturized now and all kinds of developments. We also want to get the size dependent composition if we can. So that's another field by itself of measurement. And then of course, once you collect these, either to dispose it or to process it and use it. And there's all kinds of applications for these. So from here, I just now re-illustrate that there is some kind of a feed system. There is a reactor. In this case, I'm focusing a little on the high temperature reactors, but it could be any reactor. And the capture and collection system, the measurement system. So today, I'm going to really focus on the capture and collection system, and specifically on using electrical fields. So focusing on using charge on a particle and using an electrical field to trap it. By the way, we use the same concepts in a much better and controlled manner, defined manner in designing our measurement systems. For example, the mobility particle sizes are based on some of that. But in this case, I'm just focusing on a capture and collection system and how I can enhance the efficiencies. So if I look at this device, this again is an industrial device. It's used extensively. It could be in your home. It could be used to trap viruses in an air cleaning system. It could be used, it's used all over the place, right? But typically I need some kind of a high voltage power supply, which breaks down the gas, creates a corona, as illustrated in this figure on the right, which results in large number of ions being produced. These ions then attach to the particles. As a result, the particles get charged, and then an electrical field is used to trap the charged particle, right? And of course, we want this to be a high efficiency device. It's a low pressure drop device, so it has advantages over filter type devices, both in terms of collection of wanted particles and unwanted particles, because when we are intentionally producing these, you want to also recover them and use them. And you can automate these. So if you look at a full scale system, it could be it could be as large as a building, a few stories tall, and you wrap it and you automatically drop the collected particles into a hopper and then take it out and things like that. These have been scaled up and they're extensively used. So, but if I dig in now, are they effective? Is the nanoparticle collection efficiency high? So if I look at the size distribution, and this is maybe a coal combustor. Yes, this is from a coal combustor. And of course, different modalities of coal combustion. So don't focus on the two size distributions. They're different operational parameters. But you see that there's a large concentration of particles, especially a number concentration by in the smaller sizes, even less than 100 nanometers. So a large concentration. Of course, there could be a bimodality for the larger particles, depending on what combustor we are using. But typically, because I start with a molecular state in the high temperature system, and as I cool down, we end up with a large concentration of small particles, nanoparticles, as we call them, less than 100 nanometers. And then I just re-illustrate this. This will enter this device. Hopefully, they will be carrying sufficient charge and get trapped. So if I look at the collection efficiency now, and you see the collection efficiency, and at the bottom, I just give examples of different sizes. The collection efficiency goes up and down. So this again is the mechanistic details and how effectively particles can be charged. So if the particles are rather large, they pick up sufficient charge, though they experience a large drag force opposing the motion towards the collection plate. But because they carry a large charge, they can be trapped effectively. So they are collected with high efficiency. As I start reducing the size, the charge goes down, though the drag is also going down, the charging characteristics go down, and then the efficiency drops till it reaches a point when then the drag force now, the opposing force goes down, so the efficiency starts going up again. So this U-shaped curve is rather well known, and it's a typical behavior that we see in these devices. And attention is paid, of course, to try to improve this or minimize this dip in the collection efficiency. And then if I go to very small particles, again, the charging characteristics are complex. I cannot charge them effectively, so the efficiency again goes down, though the drag force is also low, but the charge dominates. So depending on which size range I'm in, what geometry I have different collection efficiencies. So the goal is then, can we enhance these efficiencies, right? So that's a goal. So all this as an introduction. So one thing is, folks, including our group some years ago, we tried to see that could I photoionize, could I use photoionization, could I use external irradiation to enhance the charge on these particles, or create a larger ion concentration in this corona system, as a result enhance the charging of these particles and then trap them. Yes, works well. Ultimately, we came up with the use of a soft X-ray emitter to enhance charging, and we could demonstrate significant improvements in the collection efficiency. And some of that is shown here. So again, here, this is now going into the laboratory, doing a very controlled set of experiments with particles of different sizes. And as I indicated, as we go to the smaller sizes, they are very difficult to charge. As a result, the efficiency drops off, right? But when I start enhancing and adding this photoionization source, in this case, the soft X-ray, you can see that the efficiency goes up significantly. And this uncharged fraction, which was present in the absence of this photoionization, results in an enhancement of the charge and the capture. And of course, then I can tune the voltage, the intensity of the soft X-ray, and do all kinds of experiments. A very interesting thing is that I can capture particles with very high efficiency. And if you look at some of the viruses and the bioaerosols, which are problematic, are in these size ranges. So I can use it to effectively clean the air of these. I might even be able to oxidize some volatile organic species, organic compounds, and so forth. So many people are exploring these as air cleaning devices, even in residential environments. Okay, so this is all to indicate the importance of particle charging. Nanoparticles are partially charged, resulting in a breakthrough or a lower efficiency of capture. Even if I use something like an electrical field, an electrostatic precipitator, I really need to augment the particle charging depending on desired efficiencies or high efficiencies. Photoionization is one way, but the ESP itself has a corona, has a plasma. Can I integrate some concepts of a plasma, right? Even different types of plasmas to enhance the charging characteristic, which makes it then a compact system. So that's just sort of an hypothesis. Can I just play around with some of the plasma characteristics? And that is the subject of the paper that I'll describe very briefly today, okay? And of course, you have to read the paper for the details because I'll run out of time to cover every single aspect, but just highlight some of the key results. So this is study of atmospheric pressure plasma systems. The first thing is to just study the charging characteristics, right? So what is the charge state, which means both the polarity and the magnitude of particles that exit a plasma system. And in this case, it's a RF plasma, right? So it's an RF plasma using an AC voltage system. So there are different types of plasma. So we set up a very detailed system, again, starting from the left, in this case now very controlled particles that are generated. I can do that by atomization. I might want to use different kinds of particle characteristics or different kinds of particles that I generate. So we just atomize it, dry it out. And I do not want the entering particle to carry any charge, because even the process of atomization might impart a certain charge. So we use something called, what is referred here in this picture as CPR1, as a charged particle reducer. It's just a simple electrical field which will trap any charged particle. So the net is that particles that carry no charge are leaving this system. And that's what is desirable for me. So I bring in a completely neutral aerosol and send it through this plasma system. And then at the outlet, I bring in my very traditional measurement tools. I want to know the total fraction of particles that got charged in this system. So I can use a CPR2, referred to as CPR2 here, at the outlet. and then just count the particles. So that will tell me what fraction was charged compared to the inlet, and gives me a total charge fraction. I can then also measure the size distributions and so forth. I can then also use a tandem DMA system, which means that I pull out particles of a certain mobility and send it into a very conventional SMPS system, which is the DMA and the CPC. And by stepping through the voltage, I can then get the charge distribution. So this is also pretty well-established system for individuals who do charge particle research. And one can then do this study and map out how effective a plasma is in charging particles. And could I integrate this then with my ESP system, which is of course going into the applied aspects, but in this case, we just wanted to understand this. So the first paper, I'll just summarize what happens. We did observe high charging efficiencies for particles greater than 100 nanometers, but particles smaller than 100 nanometers, the charging efficiency dropped. It dropped significantly. 20 nanometers was less than 40%. And of course, tiny particles as small as 10 nanometers, the charging efficiency was close to zero. Okay, so while this is a great concept, a plasma, by the way, is a very ion-rich system, and I'll describe that in a second. The hypothesis was, hey, it's going to charge up everything, send it into a trapping device, and I've captured all my particles, right? But not so, as I'm just illustrating in that first summary point. The next thing we did is we did, of course, measure the charge distribution because we wanted to understand it in more detail. They were indeed bipolar, which means they carry positive and negative charges. We came up with a charging mechanism, a two-stage charging mechanism. We did a characteristic time scale analysis to understand what exactly was happening and so forth. So there's a very high so there are two regions as illustrated here. We call it stage 1 and stage 2. In the plasma region, there's a very high concentration of electrons, resulting in an electron flux to the particles, causing it to be negatively charged. But in addition, there are also positively charged ions. There is a region, a stage 2, which is referred to as a spatial afterglow region for the plasma. And what happens is, because of the very high mobility of electrons, right, they get removed to the surface. They're quickly lost to the walls, leaving the larger positively charged ions in the spatial afterglow region. So though particles were very efficiently charged in the plasma region, these positive ions start neutralizing the particles, right? Now, it would be great if there were not enough positively charged ions, but they happen to be there. As a result, there is a neutralization effect. The net is you still get a bipolar distribution of charges, but these small particles are not effectively charged. So, of course, we did a detailed analysis, estimation, and this paper, which is actually precedes the Aerosol Science and Technology paper, has all the expressions and estimations of different characteristic times to give a little more quantitative understanding of what I'm just saying qualitatively. Okay, so now having understood that, can I do something to this plasma system and enhance the charging? And the thought was, the strategy was, let's try to apply a DC bias, right, in the afterglow region, which will effectively remove the positive ions. So if I can scavenge out the positive ions, that's going to leave a predominance of the negatively charged particles to flow out of the system. And then I have a aerosol which is highly charged. Okay, so that was the hypothesis. And as you can see, there's again the plasma region. It's a RF plasma, but after this ground electrode, we put in a DC voltage, a DC bias. And of course, I can put a positive bias or a negative bias. And it's a negative bias that works efficiently. And this is the subject of the Aerosol Science and Technology paper. So on the left bottom, you can see the charged fraction as a function of particle size. And let's start with no DC bias, which is a conventional plasma with an afterglow region, which I just described, which was the subject of the earlier paper. So you can see that as we reduce the particle size, the charged fraction goes down significantly. In fact, I go to the smaller sizes of 10 nanometer and so, and the charge really drops off to close to zero. Okay. Now I intentionally apply a negative bias. The negative bias was applied so that there was a certain distribution of the field. The way we apply it and so forth are also important. But the interest was to see if we could scavenge the positive ions, and that's why the negative DC field helps. So here I show you only results of a negative DC bias. If I apply a positive DC bias, really we did those experiments, there was not much change, and we couldn't enhance charging. So as I keep on increasing the negative DC bias, and this is of course for this specific system, some of the dimensions are there, the detailed dimensions are in the paper. You see that beyond a certain applied bias, we call this the bias voltage, the efficiency starts the charge fraction starts shooting up, right? Around, let's say, negative 0.5 kilovolts of DC bias. And then after that, it doesn't go up significantly, but there is a significant increase from a completely uncharged particle at very small sizes to at least 40 to 50% picking up charge. And even in the other sizes, there's an enhancement in the charge. So at least empirically, it works. Of course, mechanistically, I will explain it in the next slide. But another measurement we did is to study as a function of the bias. We picked up two particle sizes, 25 nanometer and 45 nanometer. The 0 kV is no bias, so it's a conventional plasma system with its afterglow and no bias voltage. You see that the green bars are highest, so the neutral fraction is highest. As I indicated earlier, we have a large fraction charged in the plasma region, but the interactions with the positive ions then cause it to ultimately become neutral. So a majority of the particles are neutral. On applying a 0.9 kV negative DC voltage bias, you can see that the negatively charged particles begin to dominate, the neutral particles go down, and of course the positively charged particles are also low in concentration. And this is primarily because of very effectively removing these positively charged ions, allowing it or preventing it from neutralizing the negatively charged particles. And we see the same trend with a 45 nanometer particle, of course, and these are quantitative measurements. Another interesting thing for us aerosol scientists are putting combination of instruments, using them in tandem, and which allows us to really pull out this kind of a data very effectively and precisely, right? So these are results. So the hypothesis that we had, or the strategy that we had, seems to work. And if I were to then dig in a little deeper, which is described in the paper, so I now need to understand the two important aspects, right? Mechanistic details. So one is the removal of the positive ions, right? The positively charged ions. And in contrast is the neutralization time. If I don't remove them, there is a certain time constant for neutralization. Both of these are, in some case, the neutralization is not as impacted by the bias voltage. I'll describe that in a second. But the loss term, the removal of the positively charged ions, is significantly impacted by the DC voltage bias that we apply. Now, remember, the loss is a desired feature. So I would want that to be a very short characteristic time, because I'm trying to remove, I should have probably used the term tau remove, but nonetheless, this is from the paper. Tau loss is the loss of the positively charged ions. And you can see as we increase the DC bias, the characteristic time for removal of the positive ions goes down significantly. How do we calculate it? Of course, you have to map out, as I indicated, the electrical field strength and direction, right? It's a axisymmetric system. The direction of the field is equally important. It's a vector, of course, we all know that. So we use COMSOL to solve those equations. So once I get the electrical field distribution, intensity and direction, I begin to then bring in my charged ions and do a combination of drag and electrical forces and get the trajectory of these positive ions in this afterglow region where I have the DC bias. Clearly, with more bias, the field strengths go up and the removal time or the loss time goes down significantly. On the other hand, I want to contrast this to the neutralization time. And the neutralization time for the negatively charged particles, we use the Fuchs theory, with the limiting sphere approach. Some of this is described in our earlier paper. I just give you the expression. One has to, of course, calculate the ion attachment coefficients. There are some significant degree of calculations and some assumptions that go in. I need to define my plasma ion concentration estimations and so forth, but this is an intensively studied field. So we borrow from that, get that expression, and I plot the neutralization time for these negatively charged particles, right? And you can see that beyond a certain DC voltage shown by the arrow, the loss time or the removal time becomes much smaller than the neutralization time, or becomes smaller than the neutralization time. And that's when I'm going to have effective removal of the positive ions. Below that, I'm not going to be very effective. So this is a good way of comparing to the experimental trends that we observe. And it sort of matches around negative 0.5 kV. That's when we see that transition and the improvement in the charging efficiencies of the particle, right? So one can do these analysis, and then depending on the geometry, you can do calculations for your specific system. So this sort of confirms our mechanistic interpretation. And finally, we always like to illustrate with sketches and pictures. So on the left is the plasma with the afterglow region with the DC bias. You can see in the plasma zone, there's a very large concentration of electrons that are produced. There's all kinds of thermoionization, photoelectric emission, which results in particles preferentially being negatively charged. And then the strategy is to remove effectively the positive charged ions in the afterglow region. And that is illustrated on the right-hand side. If we are below that critical cutoff voltage, as I defined it, then I don't very effectively remove the positive ions. So that then still proceeds to neutralize it. or I remove only a small fraction of the positive ions, but above the cutoff voltage, most of the positive ions are very effectively removed. As a result, a larger concentration of particles with negative charges leave our system. And once I have a charge system, depending on what I want to do with these, just trap them, collect them. A simple conventional ESP is going to work well. So this is sort of the subject of this paper, was to enhance charging with the DC bias. So with that, I'll pause, because if there are any questions, we can have a little discussion, and feel free to reach out to me. My email is listed there. I again would like to acknowledge the co-authors, primarily the PhD students, Sukrant, Girish, Abhay, and then of course, collaboration with a plasma expert, Dr. Mohan Sankaran, and his student, Nebiel, several other students from the group, partial support, and AAAR again for really doing this, and in a very quick manner, maybe explaining at least the concepts behind the paper. And if you read it now, hopefully the equations would make a little more sense, and you can proceed to understand it better. So thank you again for your attention, and I'll be happy to answer any questions if there are any. So thanks, Abhay. I'll let you ask me the questions if there are any.
Yeah, great. Let's all virtually thank Professor Biswas for the nice presentation. At this point, if you have any questions, feel free to type them into the chat. At this point, we actually don't have any questions yet. Perhaps I can maybe kick off the discussion. Oh, okay. We just got a question here. I expect that charge distributions have subtle effects on coagulation mechanisms. Do you have any comments about your RF plus DC high voltage system with respect to this idea?
Yes, this is a very good question. Of course, as I said, I did a very qualitative type of presentation. Let me see if there are some equations. Okay, so you start, look, I hope you can still see the screen. So this is of course just the ion concentration equation, but the concept remains. Same way I would have a particle concentration. So N could represent the size distribution of the particles. And you look at the collision term, you see that Ni is the ion concentration. It is colliding with particles of a certain size distribution, certain charge Q. X is just the spatial dimension, and tau is of course a certain time scale, time dependence of the size distribution function. So absolutely you have to account for that. And this is where the comprehensive aerosol population balance models, the aerosol dynamic models, as we call it, to solve the GDE. And just the collision terms are complex enough that we play with it, but this sort of gives you impression. So good question, and one has to, yes, definitely account for it. And these are all lumped together to eventually get the charge distribution on the particles as a function of size, location, time, and so forth. And of course, there are other details with these coefficients, how you calculate this. The bottom is the collision coefficient based on Fuchs charging theory, the limiting sphere concept or sphere dimension, delta, how do you calculate that? And clearly there are always some assumptions, the collision efficiencies and so forth. And I'll of course refer you to the paper for some of these details. Good.
The next question, could you clarify the mechanism regarding the DC bias? Does it simply act as a trap for the positive ions?
Right, so that was the concept, that exactly, yeah. So from the understanding, we figured out that it's those positive ions that are resulting in that neutral fraction. So our strategy was, could we do something to get rid of or remove those positive ions, right? Because they go through. Now, the electrons are removed because they are highly mobile, as you know, they're much smaller, and the mobility is significantly greater than a positively charged ion, which could be an argon ion or any gaseous ion carrying a positive charge. So as a result, the strategy was, could I impose a simplistic electric field? By no means optimized. I could definitely optimize how I apply that electrical field. And that's why the negative bias field to remove that. So it's as simple as that in some sense, right? And once I remove the positive ions, the charging efficiency goes up because it can't act as a neutralizer for the charged particles, especially the negatively charged particles, right? As it goes into the afterglow region downstream of the plasma zone. Mm-hmm.
Great. Yeah, there was a follow-up, but I think you addressed that. Why would that increase the measured charging efficiency as stated?
Yeah.
Yeah.
Mm-hmm. Yeah. So it's again loss or removal of the positive ion compared to the neutralization time. And one, if all of this is verified well, one could use these as design parameters if one had to really use this, in some kind of a practical system. So the removal time constant compared to the neutralization time, and we want the removal time to be much shorter than shorter than the neutralization time.
Well, that's the last question in the chat. We still have a few more minutes, so maybe while people are thinking more questions, I can bring up another interesting topic. So obviously we're talking about small scale systems here, laboratory systems, but the intended application is to perhaps scale it up and integrate it into a larger particle control and removal system. Do you have any comments on kind of considerations that should be taken when taking a small system like this and scaling it up to something like perhaps an ESP or in an industrial process?
Right. So that, of course, is challenging. This is where I always try to look. One has to, even collaborate because there's so many practical aspects in these systems, including it's not as clean and nicely controlled as in a laboratory. But in terms of doing this, yes, so it would definitely go upstream of the ESP system, right? So design it in a manner where the high concentration particulate stream could interact with the plasma zone, but you want to then control the design of the plasma system. Now, plasma systems are being scaled up. In some sense, the corona is also like a plasma system. So there could be advantages of integration, but I won't go there. So my thought might be first is to have a two-stage system to one enhance the charges entering the conventional ESP. And that may be a first step because people who are running these systems might be don't want to disturb their own designs and things that they have to operate. So a sort of approach might be to design a pre-charger, if I might use that term, with a concept like this. And that might even allow us, if the flows are high and we need to split it, maybe we could have a series of pre-chargers. Just like in the ESP, the flow actually gets split into a number of parallel plate zones. So use a pre-charger system would be one thought, but clearly one would have to design this well, right, and actually try it out. So, yeah.
Okay. Yeah, we have another question in the chat. Is there any scenario where you would want to remove negative ions instead of positive ones?
Right. So, yeah, that's a good point. The electrons, due to their high mobility, are being removed pretty much without doing much. But because of the plasma region predominantly placing a negative charge on the particles, So another strategy which we thought about was, and that was the reason why we used a positive DC bias voltage, is to not remove the positive ions, but let them be there. But you're going through our neutralization step and then a charging step. So that might not be the most effective. So the key is, could I have a system where I have a large concentration of positively charged particles leaving a plasma? But clearly the electron concentrations are so high that dominates, and then the electrons are removed, but the positive ion. So if I use the positive bias and further removed electrons and kept we didn't see much of an improvement, right? At least very quick initial experiment. So that was the primary reason, I would say, in this system, this particular system, but would probably need to think a little more. But yes, you could play with it, enhance the positive ion concentrations and so forth, right? You also have to see how you want to operate your ESP downstream, maybe, to play with it and get the net improvement. Yeah. Mm-hmm. So maybe a better design of the bias voltage, which would retain a lot more of the positive ions, might be one approach. Yeah. Whereas this approach is not very effective. Yeah. Mm-hmm. But good point.
Well, that's the last question in our chat for now. We're almost at the top of the hour, so I suppose we could probably wrap it up here. If you have any follow-ups, feel free to reach out and ask questions. The AS&T paper is up there, so it's a great read. So yeah, thank you everybody for attending the lecture. Let's thank Dr. Pratim Biswas again for his nice talk, and I suppose we'll see you all next month for June's AS&T lecture. Thanks everyone, have a good day.
Great, thanks, thank you.